Hi everyone, my name is Azil and welcome to your first step in organic chemistry. So in today's video, I'll be talking about the introduction to this topic and just an overview of what organic chemistry is all about. So if you've ever wondered what makes up your fuel, your food, your medicines, and even plastic, organic chemistry is what revolves around all of these different types of compounds or materials. So organic chemistry, in a nutshell, is a study of carbon-based compounds. And look, they're everywhere. Your shampoos, your soaps, your painkillers, which is basically your medicines, food you eat, and even yourself, even your body, your DNA, your genes, and the different biomolecules in your body, all of them revolve around organic chemistry. The reason why carbon is so central is because it can form four strong covalent bonds. Okay, yeah, because carbon has 4 valence electrons, so it requires 4 bonds, 1, 2, 3, and 4, to form a full octet. So I've said that carbon has 4 valence electrons, and that's because it's in group 4 of the periodic table of elements. So it having 4 electrons means that it needs another 4 electrons to form a full octet configuration. So that's why you see carbon usually forms 4 bonds. So example for methane, which has the molecular formula of CH4, or even you see in, for example, ethane. So it's a 2-carbon alkane, and you can see that the carbons in this in this molecule still forms 4 bonds on each carbon itself. There are also many different other compounds such as propane and butane, pentane, which are 4 carbon and 5 carbon respectively. And these are just the basics of organic chem, and just one group of the many different groups that you find in organic compounds. Okay, now let's introduce to you what elements are there in organic chemistry that you need to take note of. Okay, so let's have a recap on the periodic table. So in group 1, you have metals like lithium, sodium, potassium, and you have, let me think, it's rubidium. Group 2, you also have metals like magnesium, calcium, barium, and beryllium. In group 3, however, we're skipping past all the transition metals, which includes metals like copper, zinc. Zinc is not a transition metal, but we have copper, we have iron, is also a transition metal, and many more. You have group 3 metals also, so this includes metals like aluminium. And then in group 4, that's where your most important molecule comes in, carbon. And right below carbon is silicon. Then you also have the group 5 non-metals. Now, what you're looking at is nitrogen as the first element. And then followed by group 6, where you have oxygen. And right below oxygen, you also have sulfur. And in group 7, these are what we call the halogens. So, namely, fluorine, chlorine, bromine, and even iodine. And then in group 8, this is not so important in organic chemistry, but it's also good to know. You have what we call noble gases. So examples are like helium, neon, and xenon. Yeah. So this is just an overview of what the different elements in the different groups of the periodic table are. And in organic chemistry, now let me tell you what are the elements that you need to focus on. Okay, and just before I forget, you also have hydrogen, which is placed above group 1 in the period, above all the elements in group 1 in the periodic table. Yep. Okay, sorry about the plus sign. But yes, the key elements you need to focus on is of course carbon, hydrogen as well. This is like, in other words, the literal, I like to call it the sidekick of the carbon atoms in organic chemistry. The other elements that you also need to take note of that partner a lot with carbon in organic chemistry are like nitrogen, oxygen, all four halogens, at least the basic four here, and sometimes sulfur. Sulfur is what makes up thiols. Nitrogen is what makes up compounds like amines and amides. And this is important especially when you're looking at proteins in biochemistry. And oxygen is also another common one. It's found in alcohols, carbonyls, and in other compounds like ethers. So this is an overview of what the important elements are in organic chemistry. So carbon and hydrogen are the top two that you focus on in this whole topic. Then now in this section, I'm going to talk about how to read or draw organic structures. So firstly, you have the Kekulé structure. And for example, if I want to draw, let's say I want to draw ethanol. To draw the Kekulé structure of ethanol, this is how you do it. So you have the carbon in the middle and the hydrogens at the side. And then you have the hydroxyl group here for the alcohol. So this is basically the so-called full structure of the compound, every atom and bond being shown. It's good for learning, but not very practical when you're talking about very big molecules, which you will see it down the road as you learn organic chemistry. Then next up, you also have the condensed formula. So let's say we use ethanol again. It will be CH3, CH2, OH. So CH3, which is this, and then CH2, which is here, and then finally the functional group, which is this. So this condenses the molecule. It saves space, but it still shows how the atoms connect in a way. And then lastly, I'm going to introduce to you the most used in organic chemistry, the one that's the most used in organic chemistry, or is what chemists use about 80-90% of the time. This is the skeletal formula. So for ethanol, for instance, is this. Each N here represents a carbon. This carbon here is bonded to the oxygen, the hydroxyl group. To help you illustrate or explain this better, let's go through a few examples. So for each of these examples, I'll be drawing all three of the different structures, the Kekulé structure, the condensed structure, and finally the skeletal structure for each of these different compounds. So let's start with butanol, or 1-butanol, basically straight chain butanol. The full Kekulé structure will look like this. It's going to look like 1, 2, 3, 4 carbons. Then you draw the hydrogens. Then you also draw the functional group. The condensed structure will look like this. Finally, the skeletal structure will look like this. Let me use a different colored pen for this. So to explain a bit more on the skeletal structure of any organic compound, each N or each band represents a carbon. This here is not a carbon because this is just representing the bond that is formed between this oxygen atom and the carbon atom here. Then you might ask me, so where are the hydrogens? The answer, the hydrogens are actually implied, or they are basically hidden. So let's say for this carbon here, we know that there's 3 hydrogens attached to it. But for this carbon here, you see that there's already 2 bonds connected to 2 carbons on this carbon itself. So this carbon should only have 2 hydrogens. So 2 bonds to 2 carbons and 2 bonds, the other 2 to the 2 hydrogens. So basically, same for this carbon as well. And also for this carbon, since it already has a bond to 1 carbon and to a bond to the hydroxyl. So now let's move on to propanoic acid. The Kekulé structure for propanoic acid is as such. It will look like, sorry about that. It will look like this. Draw the first 2 carbons, the hydrogen, and finally you draw the carboxyl group. Take note that this oxygen is doubly bonded to this carbon here. Then you also have the condensed structure, so it looks like this. Finally, you have the skeletal structure, which will look like this. Okay, maybe let's not draw it this way. Maybe I'll draw it this way, so it's a bit easier for me. So you can see, as usual, just reiterating my previous example, this carbon here has 3 hydrogens. For this carbon here, there's 2 hydrogens. But however, this carbon here, if you look at it, since it already forms 4 bonds in the diagram, or in this drawing itself, 1 here, 1 here, and 2 here, doubly bonded to the oxygen, this carbon will have 0 hydrogens bonded to it. So that's, in general, how you read skeletal structures in organic chemistry. Now let's go through just one more example. Okay, so let's say for formaldehyde, this is 1 carbon, and then you have a hydrogen, 2 hydrogens, and a doubly bonded oxygen. For the condensed structure of it is basically just actually this is the condensed structure actually. Yeah. So yeah, this is just the condensed structure for formaldehyde. It's actually already written here. But okay, yeah, but without further ado, lastly, for the skeletal structure, it looks something like this. You can see, as usual, the carbon here, it has 4 bonds already, so 2 of it to the hydrogens and 2 more of it doubly bonded to the oxygen. So there is 0 hidden hydrogens here in this compound. Okay, so this is where it gets fun. So in organic chemistry, in organic compounds, there are functional groups that basically make up the sort of the personality of the molecule. So they help in deciding its physical properties, its chemical properties, its reactivity, and other different properties or qualities that the compound will provide, and how it reacts basically, and what will it be used for. So as I draw them, I'll explain to you what they look like and where you might also find them in real life. So first off, we have the basic ones. We have the alkanes. So these are just single bonds. So for example, for ethane, or for propane. So it looks, okay, wait, never mind. Let me draw the condensed formula. So propane will look like this. 1, 2, 3. 3 carbons in its skeletal structure. You also have butane and even pentane. So they are found in fuels like they are found in examples like LPG or in gas canisters, especially compounds like butane and propane. Think of them as the backbone of organic compounds. You also have alkenes. So instead of single bonds, alkenes have double bonds. So for example, for butene, 4 carbons, but you have maybe a double bond somewhere. Maybe it can be here, or it can also be here. Unlike alkanes, they are more reactive, and they are generally used to make plastics, like for example, polyethylene. Then you have single bonds. You also have double bonds, which are alkenes, doubly bonded carbons. You also have triply bonded carbons, and these are what we call alkynes. So for example, for ethine, triple bonded carbon. And just to note, these are rare, but they are also quite reactive. Yeah, so ethine, for example, is used in welding torches. So more examples will be like, example, butane, triple bond here, or maybe triple bond here. Then after that, you have those compounds, and I mean those functional groups that don't just contain carbon and hydrogen. So one example, alcohols. They contain the OH group. So in other words, it will look, generally the functional formula for alcohols will look like this. Whenever I write an R, it's basically representing an alkyl group. So it can be like, an R can represent maybe like this, or even this. It's just to help indicate what the functional group is. So alcohols are found in, let's say for example, ethanol. So it has the molecular formula as such. You can find it in hand sanitizers or in alcoholic drinks like a beer. And even maybe isopropyl alcohol. This is found in alcohol swabs. Then other than alcohols, you also have carboxylic acids. They have the carboxyl group, which is indicated as such. And generally these are acids, so basically they readily lose this hydrogen as a proton, like any other normal acid. Carboxylic acids are generally weak, but one famous example is like ethanoic acid, or in other words acetic acid, which has a molecular formula of such. You can find this in vinegar, and that's what gives its slight sour taste in vinegar. Then you also have nitrogen containing organic compounds. One example, amines. This here is an amine group. They are quite basic. Unlike carboxylic acids, they readily accept a proton because of nitrogen's lone pair and its ability to hold a positive charge better than oxygen does. This is found in amino acids and therefore proteins, or even in pharmaceuticals. You have amines, you also have amides. It has an amide group as such, or if you want me to draw this out, it looks like this. It also has doubly bonded oxygen, but instead of an OH like a carboxyl group or carboxylic acid, it has an NH2 group here. So this group here is what we call an amide group. It's found in proteins, and it's what joins amino acids together to form peptide bonds. So other than nitrogen containing compounds, now let's go back to doubly bonded oxygen compounds with the doubly bonded oxygen. Okay, or what we call, whenever you see compounds with this group, they are what we call carbonyls. So they have, it's basically a carbon doubly bonded to an oxygen. I'll show you more examples in a bit. Okay, so one example is a ketone. So a ketone is basically a compound that has a carbon with a doubly bonded oxygen in the middle of a chain. So for example, maybe I have butanone. 4 carbons, and right here is the doubly bonded oxygen to the carbon. Yeah, you know acetone? This is a solvent that is used in the chemical industry quite often. So this is actually a ketone. And then other than ketones, you also have aldehydes. A bit different is the fact that they also have a carbonyl group, but at the end, instead of another R group or another alkyl group, you have a terminal hydrogen. They are often found in fragrances and preservatives. Then you also have, I've mentioned earlier, sulfur containing compounds, like what we call them thiols. So they are similar to alcohols, but except that instead of an oxygen, it's a sulfur atom. This right here is a thiol group. You also have nitriles, which is a group containing a carbon that's triply bonded to nitrogen. One example include your gloves that you use in your laboratory, like your nitrile gloves. Then after that, you have all these different functional groups. You also have the different kinds of carbon chains that you can find in organic compounds. So, for instance, let's say for straight chain butane, or maybe straight chain pentane. Oh wait, sorry, that was hexane. Or you have maybe butadiene, so maybe like this, butadiene. Or maybe butanol. These are what we call aliphatic hydrocarbons. They are basically straight chains. But here's the thing. These compounds can also form sort of a circle, okay, not really a circle, but a ring. And these are what we call alicyclic compounds. So for instance, cyclohexane. So you can see 1, 2, 3, 4, 5, 6. 6 carbons. So cyclohexane. And each carbon here has 2 hydrogens bonded to it. Like I said, this is the skeletal structure, so the hydrogens are generally hidden. You also have cyclopentane, which is also another alicyclic compound, a cycloalkane. Yeah, it's 5 carbons. Or another example, even you don't just have cycloalkanes, you can also have cycloalkenes. So for example, you have cyclohexene, or maybe cyclohexadiene. So double bond can be like right here or right here. You also have the smaller ones, which is the smallest alicyclic hydrocarbon that you generally see is cyclopropane. And this is very unstable because you can see that generally in carbon, in a carbon with 4 bonds, if you draw its full structure based on VSEPR theory, you should have bond angles of 109 degrees. or if I'm not wrong, it was 109.4 degrees. But however, in cyclopropane, you can see that this is not the case. So maybe for instance, for this carbon here, its bond angle here is 60 degrees. So there's this angular strain on the ring, making it very unstable and very ready to react. The same goes also for cyclobutane, which is a 4-carbon alicyclic compound. Lastly, you have alicyclic, you have aliphatic, you also have aromatic compounds. I'm not going to go through many examples of what aromatic compounds is, but I'll need you to know the most important one, which is benzene. And you can see that it has 3 double bonds in this 6-carbon ring. You can also draw it this way, where instead of drawing the three double bonds as such, you can draw it with a circle in the middle. As to why this is drawn like this is because of what we call resonance, which I'll explain again in a later topic. This is what contributes to the aromacity also of benzene. So benzene is generally, because of resonance it's stabilized, and therefore you find that it's not that ready to react. And usually when you react it, maybe let's say you want to form toluene, for example. Usually you need a catalyst like aluminum chloride. Yeah. And there are also many other derivatives for benzene, such as phenol, or you also have aniline, which has an amine group. Okay, wait, let me just write down the names of the compounds real quick. This is toluene, this is phenol, this is aniline. Yeah, and these are just some derivatives of benzene itself. So there are also other groups like let me think, what was I missing on? Right, okay, let's go back to the different groups again. We have thiols, we have nitriles. We also have ethers. So they have an oxygen in the middle of a carbon chain. So this, for example, is an ether. You can see that the oxygen is right in the middle of this chain. So in general, this is how it looks like. Note the oxygen in the middle. You also have esters. So esters are generally carboxylic acid derivatives. Instead of having an OH group like this, it has another R group here. Yeah. So for instance, you have ethyl acetate. This is an example of an ester. So these are just an overview of what the different organic compounds are in organic chemistry. I'll go through them more in detail as I make more videos on this whole topic. And I'll also go through what their reactions are and their physical and chemical properties and what determines them. I'll also go through different topics like resonance, acidity, basicity, and also the different reaction mechanisms such as the big four like SN1, SN2, and even the elimination reactions like E2 and E1. This is just an overview of this whole topic. Thank you for watching, and I'll see you in the next video.